Hi guys!
Alright guys, welcome back to another post-lesson video. So take out that piece of paper that we're using for last week and let's start again. Alright. So in today's video, we're going to learn what are the factors that actually affect rate. So just to remind you what we learned in Sec 4, for two reactant particles to actually react correctly, the collision needs to be effective. Okay. Now Mr. Long, run me through the conditions.
So let's imagine you have two pieces of Lego as a reactants.
Okay.
If you want them to react, we want them to click together.
Oh yeah, correct.
Okay.
Yeah.
So how do you make sure that we click together? You must make sure that the Lego must be in the correct orientation, right?
Okay.
You cannot click it in a certain way because the certain way the Legos will not link together. So we have to make sure that they are in a certain orientation, then it will start to click together.
Perfect.
And that is like a reaction, right? Now the second thing that's important over here is when you push them together, right, you need to apply a certain amount of force, right? You need to apply a certain amount of energy before they can really stick together. So what is that kind of energy in the chemistry context?
Well, activation energy.
That's right. So therefore, in general, if for collision to be effective, you need two things, right? You need to have a correct orientation. You also need to have enough energy.
Whoa, Mr. Long, you're speaking very, very fast. You okay?
Yes, sorry. It's very hot in here. So it's like I'm the particles, right? The hotter I get, the faster I speak.
Oh, so that reminds me of the factors that affect the rate of reaction.
Oh, okay.
Right? Now, guys, instead of you guys just memorizing this blind, right? Recall what you have learned in rate equation. So from the rate equation, you can tell the factors that actually affect rate. So what I'm going to have for you here is this. We have this very simple reaction, CO plus NO2 give you CO2 and NO. Now I'm going to assume this reaction is elementary. That means one step, okay? So it's a one-step reaction.
So what's so special about one step is the fact that if I look at the overall equation, the order of the stoichiometry of the reactants actually corresponds to the order of reaction in the rate equation, right?
Exactly. So this is how your rate equation is written, right? And I won't repeat this. Now, again, you're going to look at this rate equation and see how the factors, or what are the factors that affect rate. So the first one is pretty clear, Mr. Long. Can you see how the concentration of CO and NO2 is in your rate equation? So obviously,
your rate is going to be dependent on the concentration of the aqueous reactants.
Exactly.
Right? So one of the small things that's important is that not every reactant will affect the rate. So certain reactants, the rate is not being changed at all. Why is that so?
Well, the order of reaction. So if the order of reaction with respect to that concentration is 0, then no matter how much I increase, my rate doesn't change. Okay?
That's right. So we say that the rate is independent of that particular reactant.
Now, Mr. Long, you said aqueous reagents, right? So what happens if my reagents were in a gaseous state?
So we can also consider the idea of a concentration in gaseous systems, but that is going to be a different concept. It's going to be known as a pressure. So it turns out pressure will affect gaseous systems. In this case, they are all gases, right? So therefore, definitely we can also discuss this thing called partial pressure of the reactants.
Exactly. All right. Now, the last two here is a little bit tricky because there's one more factor that also affects my rate, which is the rate constant K, small k. Now, I hope you guys have seen this in class before. We know that K is affected by activation energy. And it's also affected by temperature, right? So when I increase my temperature, you will
cause your denominator to be bigger, right?
Yeah.
But because it is raised to a negative power, that also corresponds to K increasing as well.
Yeah.
So it's a bit mathematical, but I think logically speaking, increased temperature, I speak faster, the K will increase, the rate will also increase
That
as
makes
well.
sense. So when I increase temperature, you would see how my rate of reaction definitely increase. Why? Because my rate constant is increasing, right? And yes, there is no effect on activation energy because activation energy is only affected by the presence of a catalyst. Okay, and what does a catalyst do to the EA?
So the catalyst will always lower EA.
Okay, so again, when I lower the EA, again, because of that power there, some complicated math, all you need to know is that when the EA drops on the numerator of a negative power, whatever that means, your K will go up. Okay, so you will see when I use a catalyst, my rate definitely goes up. Why? Because my rate constant increases due to a decrease in the EA. Okay?
So the last two factors, the change in temperature and the presence of a catalyst, one of the things that you must learn how to do is to explain how does it affect the rate through the use of a Maxwell Boltzmann distribution curve.
Wow, sounds complicated, right?
Of course it is.
Yeah, so come, let's talk about it. This is a Maxwell Boltzmann curve. Now, first things first, let's understand the axis. Yeah?
Yes.
So the y-axis is the number of molecules and the x-axis is energy. Now, I'm going to run you through what this means. That means this. If I fix my coordinate at one point, this tells me that at this particular point, I have this number of molecules with this fixed amount of specific energy. Let's call this 10 joules, for example. All right? So at that point, I have this number of molecules with 10 joules. Now, Mr. Long, before we continue, There is something that doesn't look quite right with this curve.
Yes, so I think it's the starting point of this curve.
Yeah.
The curve seems to be starting at, it's like floating, right?
Yeah.
And that should not be it. So in exam, you have to make sure that the starting must always be from the origin, right? The idea over here is that there are no particles, they have no energy. There's no way to get a particle that's perfectly still. The particles will definitely vibrate about their fixed positions, right? At the very least. So therefore, the graph must always start from the origin.
Exactly.
Okay.
All right.
The next idea, Mr. Tim, I'd like to ask you is, you shade an area under the graph.
I did. Can
you tell me what that represents?
Well, so by shading an area, that means this, right? So for example, if I shade this area here, I'm telling you this, the total number of molecules with energy from 0 to 10, all right? So total number is basically the area of what I've just shaded, all right?
Yes.
So for example, again, some math, if the area is 100, right, that means there are 100 molecules of energy ranging from 0 to 10.
Okay.
Okay?
Great. So now that we've understood what's the significance behind the Maxwell Boltzmann distribution, we can take a look at how a change in temperature can now increase the reaction rate.
Yes.
Okay. So let's take a look at a higher temperature. So assume that the original graph is T1, and I'm going to look at T2, which has a higher temperature. Mr. Tim, can you run us through how should the graph look like now?
All right. So at a higher temperature, that means now your graph will be lower, but more shifted to the right. All right. So it looks like this. Now, and I'll explain to you why. Because when you increase temperature, now there'll be a greater number of particles with higher energy, right? So if I look at this, if I shade now for you, if you look at this, I'm just going to look at this region here, and if I shade this region, you will see that for the temperature T1, the area at higher energy is smaller than the area for a T2 graph. You can see that, all right? So this brings me back to the whole idea of activation energy. We're going to focus on the activation energy because we know if there are more particles with energy greater than the EA, then the reaction will be
faster.
Yes. So again, let's focus on the activation energy point. We have this. So for a temperature of T1, the area is just here. So all of this area is the number of particles or number of molecules having energy greater than the EA. All right. Now I can do the same thing for T2. Now bear in mind, T2 is a higher temperature. So again, the area will now be larger, and I'll shade it in this way. All right, so you can see, Mr. Long, is the area greater or smaller?
Definitely greater, right?
Obviously greater, okay. Now, Mr. Long, there's also one more thing that students must write when they are doing a Boltzmann curve. What is that?
So as you're labeling the area, you shaded it in different manners, right?
Yeah.
So you definitely have to put in the legend, right? So we're written it on the left. So try to shade it in different manner. One is a diagonal that is one way, and the other one is the other way. So please label it carefully. We are talking about T1 and T2, the difference in them, okay? Lastly, the most important thing is always to explain what the graph is trying to illustrate. So these are the 4 points that are more important, that are most important. An increase in temperature always increases the kinetic energy, which means that there's going to be more particles possessing energy beyond the activation energy. So that actually translates to an increase in the frequency of effective collisions, which eventually ends up with an increase in the reaction rate. Okay, so the 4 points will give you the 2 marks eventually.
Perfect.
Okay, so it turns out the Maxwell Boltzmann distribution curve can also be used to explain how come the presence of a catalyst can increase the reaction rate. Okay, so we're going to take a look at the second graph. Now in this case, the shape of my curve will not change anymore because the temperature never changed. Okay, we're using the same graph, and what's going to happen is in a catalyst, right? Can you tell me what does it do to the activation energy?
Right, it lowers it, right?
Yes, so it has something to do with this vertical line that you see here. The activation energy here is going to get lowered. So it's going to shift left or shift right?
Well, lowered, so shift left.
Yes.
Yeah.
So we're going to draw a new vertical line, and I'm going to call this new activation energy EA prime. Okay, so we are always interested in particles that possesses enough energy, more than activation energy, right? So what we're going to do, Mr. Tim?
So again, we're going to shade the area of the particles with energy greater than the EA.
That's right.
And how we do that? We just go to the
right-hand
side of the EA.
Yes, and you shade it in a different manner, right? Once again, the reason is because you want to make sure that the legend, you clearly define which part is the particles beyond EA, and then the other one is the particles with energy beyond EA prime. Okay, so once again, put in the axis, put in the legend as well, and then we are going to have 4 points that give you the last 2 marks, right? So the 4 points are written on the left. First, you must tell me a catalyst has lowered the activation energy, following which you tell me that you're going to increase the number of particles beyond activation energy, which increases frequency of effective collisions as well as the reaction rate.
Yes.
Okay, all right. Now, Moving on, we're going to delve more into the idea of a catalyst. So everybody knows the definition of a catalyst, right?
Yeah.
Can you run us through it?
Well, sure. So a catalyst is a substance that increases the rate of reaction, right, by lowering the EA, but it remains chemically unchanged. Now, in A levels, we have two types of catalysts. We have heterogeneous and homogeneous, okay? Now, heterogeneous catalyst means this. The catalyst and the reactants, they're in different phase.
Oh, what is a phase? Is that your two-phase idea, left phase and the right phase?
No, not left phase and right phase, okay? Phase means they're in different layers, okay? So, for example, oil and water, now, they can be in the same state. They're both in a liquid state. But you can see how oil and layer, do they mix?
No, they don't.
No, they're immiscible layers. So the two layers are separated. This is what we call different phase.
Right.
Okay?
So if you have a different state, can I say that there are different phases?
Oh, definitely, for sure. Right? So solid and liquid, liquid and gas, all in different phase. All right? Now, so if you zoom in into this with me for heterogeneous catalyst, page 106, now you can see how all these catalysts here, they're all in a solid state, and all the reagents for the reactions they catalyze, they're all in different states, all right? And I won't highlight everything for you, all right? So again, when the states are different, the phase will definitely be different, all right? But again, remember, phases can be different if the states are the same, all right? Now, so to understand better how a heterogeneous catalyst works, you need to first understand the whole idea of adsorption theory. Now, adsorption theory undergoes 5 different stages. So we have diffusion, absorption, chemical reaction, desorption, diffusion. Oh, it's quite a mouthful. Now, how we're going to start off is like that. So imagine I have a bed of catalyst and your reagents will diffuse onto it. Now, when it diffuses onto it, Mr. Leong, does it form bonds or does it break bonds?
Definitely form, right?
Yeah.
They have to hold on onto the catalyst, right? So that process is known as adsorption, right? It's AD, not AB.
Yes, not AB, adsorption, all right? And like what Mr. Leong said, we form bonds. So you can see here, and I'm going to highlight this with you. Reactant molecules are absorbed, forming weak chemical bonds. Okay. Now, Mr. Long, remind me, just help me out. When I form bonds, does it release energy or does it take in?
Yes, release energy, right?
Yeah, release, right? So again, when I release energy, you can imagine all these bonds that I form, you release energy to weaken the covalent bonds that we have there. So you can see how the H2 bond is kind of almost breaking off, and the same thing, that C2H4 used to have a double bond here, that pi bond in green, now it's gone. Right? So really form bonds, release energy to break bonds. All right? Now, so after adsorption has taken place, you can see how now, Mr. Long, the reactants are much closer to each other. So when they're a lot closer, is it easier to form new bonds now?
Yes, because you increase the surface concentration, right?
Yeah.
So you are orientating the molecules in such a way that they can facilitate the formation of new chemical bonds that helps you to form the products.
Exactly. Okay. So the next stage is chemical reaction. All they need to do now is just form bonds. Okay. So because they are so close to each other, it's so easy to form bonds. The EA is now lower. Right, and that's it. So again, when I form bonds, I release energy. Bonds must break. So you can see how this is completely broken. This is completely broken off. All right, and that's it. So once I have this, this is finally my product molecule. So all that needs to happen now is for desorption to take place. So desorption is just the opposite of adsorption. So you just dissolve, you just remove. All right. So you can see this part. Last part, the weak chemical bonds between the products and the catalyst are now overcome. Now, small things that I want you guys to note here before we move on into homogeneous is also this. Now notice how when you form bonds during absorption, the bonds need to be weak. It is very important for them to be weak because, Mr. Leong, if these bonds that we form, right, if they are ridiculously strong, then do you think the desorption can take place?
It's going to be quite hard, right?
Yeah.
Because you need to supply quite a bit of energy to overcome these very strong bonds.
Exactly. So you need to settle in, boop, and when you form your product, you just ploop out.
Yes.
Okay, and that's it. All right.
Nice. So next, we're going to see the comparison of the other kind, which is called the homogeneous catalysis. And that is going to be where your reactant particles, as well as your catalyst, they are all going to be in the same phase, not same state, but same phase. So I'll give you an example over here. We're going to take a look at a reaction between your iodide, as well as your S2O82-, that's called peroxyl disulfate. This particular reaction actually is a very difficult reaction to happen.
Yeah.
Can you suggest a reason for that, Mr. Tim?
Well, I see how both the species, right, they're actually negatively charged.
Okay.
So if I take negative charge and I force them together, they will repel.
Okay, so that is going to create very high activation energy.
Yep.
You need to supply a lot of energy to overcome the repulsion so that the two particles can even come close together, right? So you say that, okay, this is very bad.
Yeah.
So I think what I'll do is I will probably put in a catalyst so that it doesn't have this kind of phenomenon happening. So what I'll do is I'll introduce a catalyst which is Fe3+. So it turns out, instead of having just a one-step reaction, the Fe3+ is going to create a two-step mechanism, right? And the two steps are going to be shown over here. In the first step, you now notice that the Fe3+ will participate in the reaction and is going to react first with an I-. Now this is fantastic because if I take a look at the two reactants, these two particles are oppositely charged. So this means that there's going to be attraction within them. So that is why you do not see high activation energy anymore. Yep. You are actually going to lower activation energy.
Exactly.
And because of that, you are taking a two-step mechanism. You are going through an alternative pathway, right? So that's exactly a definition of a catalyst.
Beautiful.
Okay. Following which, in step 2, you generated an Fe2+. The Fe2+ will then react with peroxyl disulfate. Once again, this is a reaction that has oppositely charged ions. And of course, that is going to create attraction, which once again, the activation energy is going to be low.
Okay. So again, just to remind you guys how a catalyst, right, consumed at the beginning, regenerated at the end, and the Fe2+, Mr. Leong, is your?
Intermediates.
Yeah, intermediate. So what we're going to do here with you is this. So I have this energy profile diagram, again, energy against progress of reaction. So this energy profile diagram is to simulate the overall reaction with no catalyst, let's assume first. And yes, like what Mr. Leong and I discussed, the EA will be ridiculously high. So I'm going to write here that the EA is for the uncatalyzed reaction. Now, when the catalyzed reaction happens, like we said, it splits into two steps. We are going to assume that the first step is slow and the second step is fast. Okay. All right? So first step, if it's slow, Mr. Leong, how does the EA?
So slow steps always have the largest EA, which means that it's going to correspond to the longest arrow. So the first upward arrow must be longer than the second one. Okay? So there you see it. Mr. Tim is going to label in for me the activation energy. Okay? Now, bear in mind that a catalyst do not change the enthalpy change. So therefore, you see that the delta H, the downwards pointing arrow, is going to remain as long, equally long as the one that is uncatalyzed.
Perfect, perfect.
So there you have it. Okay, so this is the catalyzed version, right? One of the important things to do is always to go and label in your species. So I'm going to give you 5 seconds. Go stop the video, write in the species, and when you're done, you can check your answer with us. Okay, so take a look at the answer. So a few things to pay attention to. Number one, do you put in the catalyst? Okay, the two Fe3+ must be inside the species as well. And also to make sure that those that did not participate, like S2OA2- did not participate in the first step, it must be presented there nevertheless. Okay, do not miss out any one of those because you can get penalized for that. Okay? All right, moving on to the next idea of autocatalysts, right? There is going to be another type of catalysis. So this is a very special case. Now this is quite interesting because if I take a look at this reaction itself, turns out one of the products that is being produced in the reaction is going to catalyze the reaction that produces it. And that is the definition of an autocatalyst. Okay, so the classic example over here is manganate reacting with ethane diolate ions. The Mn2+ is a transition metal ion, so those act as very good catalysts. Turns out it's going to catalyze the reaction that produces it. Okay, Mr. Tim, can you run us through the graphs that you are expected to know?
Yeah, so you need to know two graphs, concentration against time and rate against time. All right. Now, here's the thing. Remind me again, we have learned this in the start of kinetics. For a concentration time graph, your gradient at every single point of your graph reflects your
rate.
Okay. So now I'm gonna focus on 3 points here: point 1, point 2, and point 3. All right. Now again, to find the gradients, you need to draw tangents. So I'll draw tangents at 3 different points: point 1, point 2, and point 3. Now, Mr. Leong, I want you to see how the gradient at the beginning is very gentle. Right. And as the reaction proceeds with time, the gradient becomes
steeper and steeper.
Yeah. And then all the way towards the end, it goes to 0 again.
Yep. It becomes more gentle until it hits a horizontal line, right?
Yep. Then it becomes horizontal and the reaction ends. Okay? We're going to try to explain this, all right? So at the beginning of the reaction, now understand with me, like what Mr. Leong said, the product Mn2+ is your catalyst. So at the start of the reaction, you have no catalyst being produced yet, there's no product, so the activation energy of the reaction is high, the rate is very slow, right? So it's a very slow rate of reaction, very gentle gradient. Now as the reaction picks up though, and you get more and more products, so again, the concentration of the catalyst now goes up, you have more and more catalysts, and hence the reaction speeds up, okay? So the rate is increasing, as the reaction proceeds. Now, towards the very end, now, Mr. Leong, can we explain this weird little phenomenon? Because I would have a lot of products, right, at the end, a lot of catalysts. So why is my reaction so slow?
Because you're nearing the end of the reaction, because all the reactants are getting used up.
Okay. So all the reactants, the concentration of the reactants is basically close to zero, all right? And again, since rate is proportional to concentration, we have learned when the concentration of the reactants of either one involved in the rate equation is zero, the rate becomes zero, okay? Now, what we need to do here is translate all these 3 points into a nice curve, a rate against time curve. So again, let's follow the points 1, 2, and 3. So at the beginning, the rate is very slow. So you can imagine a slow rate of reaction is almost negligible, a very, very slow rate of reaction. And as the reaction picks up, so this is point 1, as the reaction picks up, it becomes faster and faster. So the rate goes up faster and faster. And then towards the end, it should drop, right? So it goes to 0 and point 3 and plummets, okay? So this is point 2 and this is point 3. There we go.
That's nice. So bear in mind that at the end of the day, when the reaction is complete, your rate must hit 0. Okay, and of course the starting point must also be 0, right?
Yes.
At the start, we're saying that no reactions begin, so that's why you start off at 0 as well. Okay, so the last part of catalyst is to look at this very special kind of catalyst called an enzyme, right? So enzymes are what we call a biological catalyst because they only catalyze biological reactions. So this brings me to my first point that enzymes are very specific. Okay, they can only catalyze a specific class of reactions. Other than that, if they are not the correct class, then the enzymes will not work. So different enzymes will work for different types of reactions. Okay. Now, how does an enzyme work? So basically, an enzyme is just like a globular protein. You're going to have a part of this enzyme, right, that allows your substrate to bind to. So that particular location is called the active site of an enzyme. Okay, so when the reaction begins, the substrate, which is a reactant, is going to bind to it. Your enzyme will induce some chemical reactions in the substrate, and as a result, your substrate is going to turn into the products, right? And as you form the products, the enzyme say that, oh, I'm done. So therefore, they release your products into the environment, and that's how your enzymes work.
That's nice. That's nice. Now, to better understand the whole idea of enzymes, we also need to understand how concentration of the reactant or the substrate, how it affects your rate. Okay, so this is how the curve looks like. So rate against con of substrate looks like a very simple, innocent-looking curve. Now, but to better understand this, we need to remind ourselves what we learned at the beginning of kinetics. For a rate against concentration curve, how does it look like?
Right.
So you need to first look at your order. So what I have for you here is this rate equation. Rate equals to rate constant times substrate. Now, Mr. Leong, if the order of the substrate with respect to the reaction is 0, so how does my rate look like?
So we say that the rate is independent of the concentration of the substrate. So that's going to be a horizontal straight line.
So rate is just your rate constant, K, so that's it. Now, if the order of reaction with respect to the substrate is 1, so again, this doesn't cancel off anymore. So you can see how this looks like a Y equals to mx curve. Right,
yes.
That cuts through origin.
Yep.
So you will get a upward sloping curve that cuts right through the origin. That's it. Now we're going to take these two pieces of information and we're going to plug them into this idea.
Right.
Okay?
So I'm going to use an analogy here. So imagine now Mr. Tim, he's going to be a manager of a fast food chain.
Okay.
Right? So he's going to set up his new store that has only 3 cashiers. Okay. Today is his soft launch, is welcome day. So he opens his doors and the customers start streaming in. Okay. So with the energy over here is this, he's going to make money, right? So that is going to be talking about the rate of the reaction.
Yep.
Right. His cashiers, the 3 cashiers, are going to be the catalysts. They are helping Mr. Tim to earn more money, right? So as the first customers come in, right, they're going to buy food, they're going to go into the first cashier, so you can generate money, right? If there's one more customer that comes in, you are going to go to the second cashier and you're going to generate more money. So in the context of the graph, right, you're telling me that, hey, if there are more customers, which is more substrate, you are going to see that the rate of making money increases. So in this case, we're going to say that it's going to be first order. So Mr. Tim, if it's first order, how should the graph look like initially?
Well, again, if it's first order, it should be an upward sloping curve.
Yes.
That cuts through origin. So you can see, kind of looks like an upward sloping curve that cuts through origin at the beginning.
That's right. Okay. Now, imagine now he's approaching peak hour, but it's lunchtime already. You start to see more and more people coming to try his burgers, right? His milkshake as well. So as this happens, right, you're going to see more people coming in. So the next customer that comes in, perhaps he'll go on to the third cashier, which is still helping him to make more money per unit time, right? So of course the rate of reaction is going to increase. But if you start to see more customers coming in, people will have to queue up already, right?
Yeah, correct.
That's right. So at the point of time, you're not making more money. Are you still making money? Yes, but the rate of making money will no longer increase. So you start to see that the rate of reaction is going to start to plateau off, right? And you're going to also, in analogy, you're going to start to see people queuing up. There's going to be longer and longer queue. So the question here is this, Mr. Tim. Have you stopped making money at that point of time?
No, we have not. We're just still making money,
Yes.
but the rate is fixed.
Yes.
Yeah?
So you're still making money, it's just that your rate of making money is not increasing. So Mr. Tim, if you want to make more money, what should you do?
Hire more cashiers.
Hire more cashiers. You should have more enzymes. So for those that do bio, you say that at this point of time, your limiting factor is going to be your substrate concentration. In order to increase the rate, you have to increase other factors such as enzyme concentration.
Exactly.
Okay. So as you go towards this saturation point, can you tell me what order is this?
Well, again, you can see how this part of the curve now kind of looks like a zero order reaction. All right. So we see it like this way, right? At the beginning of the reaction, your order of reaction with respect to the substrate is 1, okay? And at the end of the reaction, the order with respect to the substrate is 0. So in between 0 and 1, we call it a mixed order between 0 and 1, all right? So we say for a rate against substrate, the order of reaction with respect to the substrate for the entire reaction is a mixed order.
Yep. Okay. So in exam, you have to be able to replicate this graph. That's number 1. And of course, number 2, you have to explain this graph. So we have broadly divided this into 3 parts. The first part is a first order. That's where the active sites are not used up yet. So any increase in the substrate concentration is going to result in an increase in rate. But as you have more and more substrate concentration, you are telling me that the active sites are getting more and more used up. And finally, eventually, when you hit zero order, all of the active sites are used up, they are saturated. Even though you added in more new substrates, the reaction will not happen. You have to wait for existing reactions to finish before your new substrates can react.
Exactly.
So that's it for the whole of kinetics, right? This is going to be on catalyst specifically. So once again, if you have any questions, feel free to ask us in class.
Okay.
See you guys. Bye.